The Taylor series is probably one of the most useful mathematical results that you'll ever learn. It's part of a wider class of methods called series expansions, which are techniques for re-expressing an unknown or inconvenient function as the sum of terms with nice properties. In the case of Taylor series, the nice terms are taken to be polynomials of the form x to the n. Later, you'll also learn about Fourier series, which use trigonometric terms. Series expansion techniques have many applications, including stability analysis, solving differential equations, and a whole array of numerical methods for finding approximate solutions. Fourier series can also be used for storing and transmitting data and for image processing. A neat example using Taylor series is shown in the video entitled Solving the Pendulum by Series Expansion. In that case, we have to integrate a problem of the form given here, in which g of x is some function. We tackle this problem by first rewriting the integrand as a more accessible power series in g of x. The expansion is only valid when g is small. It's an example of a Taylor series expansion in G. In this video, we'll have a look at the mathematical basis for the Taylor series, which is concerned with expressing a function f of x as an infinite polynomial series of the form given here. In which c subscript n are constant coefficients and a is also a constant. Equivalently, this series could be re-expressed in the form given here. But we'll see that it's much more convenient to use the form given here, which we'll refer to as expansion about x equals a. I'll call the polynomial p of x to distinguish it from the function f of x which we're trying to approximate. Written out as a list of terms, we have the expression shown here. Our goal is to ensure the best possible behaviour at x equals a, and this is done by ensuring that p of x and its derivatives agree with f of x at that point. The conditions can be written in this form here, in which this bracketed superscript notation here denotes the nth derivative. Formally, it can be shown that these requirements uniquely ensure that the error in the degree k expansion approaches 0 in the limit x tends to a. The proof, which relies on L'Hopital's rule, is not given here. First, we ensure that p of a equals f of a, and since all of these terms go away when x is equal to a, this gives us the result that c0 is just equal to f of a. Now let's calculate the derivatives. You could do this systematically for p dash of x, p double dash of x, and so on. But I'll write down a result for the kth derivative straight away. Notice that if I differentiate the first term once, it goes away. If I differentiate the second term twice, it goes away, and so on. So the non-zero terms in the kth derivative all come from this part of the expansion. By the chain rule, every time we differentiate an expression of the form x minus a to the n, we bring the power down the front and we decrease the power by 1. So differentiating this term k times, we obtain k factorial times ck. For the next term, we'll have a factor of x minus a left over, and at the front we'll have k plus 1 factorial over 1 factorial. The next term gives k plus 2 factorial over 2 factorial times x minus a squared, and so on. Applying these conditions now for the kth derivative, we can see that when x equals a, all of these terms go away, and so this gives us the result for the kth coefficient. Using these results in the original expression gives us the complete Taylor expansion. Let's have a look at an example for the case when f of x is equal to sine x. I'll expand about the point a equal to 0. We need to calculate the derivatives at this point. We have f prime of x is cos x, f double prime is minus sine x, f triple prime is minus cos x, and when we differentiate again we'll get back to sine x, and so the pattern repeats. Substituting these results into the Taylor series formula, we have p of x equals 0 plus 1 lot of x minus 0 plus 0 lots of x minus a squared plus minus 1 lots of x minus 0 cubed over 3 factorial, and so on. We can spot the pattern, and we can write this more neatly as a single summation. If you remember how to use the ratio test, you can verify that this series converges for all values of x. In general, however, the Taylor series does not guarantee convergence, except at the limit as x tends towards a. Even when the series does converge, there is no assurance that it will converge to f of x. After all, we have only enforced the goodness of the expansion in the immediate vicinity of x equals a, in this case x equals 0. Let's plot the series expansion for sine using only a few terms. This is called a truncated series expansion. The graph here compares the exact value of sine x with the one-term expansion between x equals minus pi by 4 and x equals pi by 4. We can see that the approximation remains reasonable over an appreciable range of values. This accounts for the widespread use of the small angle approximation, sine theta is approximately theta, which you may have seen previously. The approximation can be used to rewrite the simple pendulum equation as theta double dot plus g over L theta equal to 0, which is a linear ordinary differential equation with constant coefficients, and it can be solved explicitly. Now let's investigate what happens to the series approximation for sine as we add more terms. Here's the result for 2 terms, 3 terms, 4, 5, 6, 7, 8, 9, and 10 terms. As we increase the number of terms in the expansion, the behaviour can be seen to improve and the range of appreciable agreement increases. It looks as if we might be able to get the series expansion to coincide with the function for arbitrary x values simply by taking enough terms. But is that really the case? To answer this question, we need to find a way to quantify the size of the remainder in the truncated series expansion for a given value of x. That is, we want to estimate the result for f of x minus pk of x, where pk of x is the degree k polynomial. The proof of the result is non-trivial, but is given in a separate video if you're interested. In fact, the result can be expressed in different ways, but I'll give the Lagrange form of the remainder, which states that the remainder in the degree k Taylor expansion of f of x about the point x equals a is equal to x minus a to the k plus 1 over k plus 1 factorial multiplied by the k plus 1's derivative of the function evaluated at some point xi, where xi is in the range from a to x. So to prove that the series expansion converges to f of x, it's then necessary to show that the limit of this result approaches 0 as k tends to infinity. Some functions satisfy this result only for a range of x values, whilst others satisfy the result everywhere. Functions which exhibit convergent Taylor series everywhere are called entire. Examples of entire functions are sin x, cos x, and e to the x. The natural logarithm is not entire, and a Taylor series for this function cannot in fact be constructed about the point x equals 0, since the function contains a singularity there. The result can also be used to derive an upper bound for the size of the error in the expansion for given values of a and x. For example, in the series expansion for sin x about the point x equals 0, we have the result that the remainder in the degree k truncated expansion is equal to x minus 0 to the k plus 1 over k plus 1 factorial multiplied by the k plus 1th derivative of sin x evaluated xi. Now the k plus 1th derivative of sin x alternates between values of plus or minus sin xi and plus or minus cos xi. And since all of these functions are bounded by plus and minus 1, the k plus 1th derivative at any point is bounded absolutely by 1. Thus, in turn, the remainder is bounded absolutely by this part of the expression. In most scientific computing applications, as well as stability analysis problems, we will be using Taylor series expansion only to tackle problems where x minus a is small, i.e. in the range from 0 to 1, and typically much smaller than 1. In that case, the Lagrange remainder theorem guarantees that the series converges to f of x as long as the derivatives remain finite.